Yeah, take it away, Jesse.
So I'm Jesse Spencer-Smith, and I'm Chief Data Scientist at the Data Science Institute. And I'm going to be talking about one of those kind of messy real-world applications of this. And I'd like to start just by telling you a story about what started as a consult and then turned into a really interesting project. So this all started with a consult that we had. This is a half-hour, hour-long conversation around issues or opportunities that researchers have that might involve data science, but they're unsure. So sometimes they'll come to us and sort of to talk through. And we had a conversation with Professor Marcus Eberl, who's Associate Professor of Anthropology. He's an archaeologist. And this story serves as a really excellent example of the idea that the format of the data and the way that you're going to be storing your data really is intimately tied and dependent on the use that you'll have for that data. So Professor Eberl had really interesting problem that he was working on. And can you all see my the map here of Nacimiento? This is a Mayan society. It was a Stone Age society, and there are very, very few remains. One of the interesting things was that because it was a Stone Age society, turns out that there are leavings of stone knapping, that process of actually creating stone tools. And so the problem was this: in which of these buildings was the kitchen? Because that's often where you would actually do your work, apparently, and create your stone tools. Were there areas where there was more stone tool creation than others? Well, it turns out that when you're creating stone tools like the ones that you're seeing here, you actually have some leavings. So as you're chipping away and creating your stone tools, you have, of course, the tool, and then you have these larger chips that are left behind. But those larger chips tend to be picked up by the stone knappers because they're very sharp. You don't want your kids running around and stepping on this. But what's left behind is even smaller particles that apparently are lithic microdebitage. And these are 4 millimeters, or they're very, very small. And the way that Professor Eberl had gone through and worked with this was to actually take a microscope, take a scoop of soil, under a microscope, look and identify those particles that were actually leavings of this stoneworking, and determine whether it was soil or the leavings of the stone knapping. Now, there are only going to be about 100 particles out of 1 million particles of dirt. So this is painstaking work, and you might only find a couple of dozen in any sample that you might take. But Professor Eberl had a remarkably brilliant idea, and that is he bought a particle analyzer. So the particle analyzer, you take a scoop of soil, you put it in here, and it comes up with a whole list of properties of this soil. And so you're able to actually look at this and then see all these different measurements. So it takes measurements of the shape of the soil, how transparent it is, how round it is. So you have all these measurements that you can take of the soil. So he came to us because he knew that he'd have to do a lot of analysis of this to determine from these numbers what was soil and what was lithic microdebitage. And he came to us with a question: how do I store all this? I think I need a database because we're going to have many millions of these lines. Anybody know what the limit in Excel is? How many lines you can have in Excel? Yeah, it's 1 million, and you're done. So even if you before you get to 1 million, it's going to stop performing very well. And so Excel was not an option here. There are going to be millions of these, and he was unsure how to store it. Well, we started to think about it, and I asked just to take a step back. What is it actually that you want to do with all this data? And that's when he took me through and he said, oh, I do this type of research, and I looked under the microscope before, and now I have a particle analyzer. This is what I want to look at. Well, it turns out that the problem that he was trying to solve was really important, and that is he wants to tell the particles apart. This turns out to be a machine learning problem or a deep learning problem where you're going to be doing learning on all of these. And another brilliant thing that he did was he hired a stone knapper to create stone tools for him. They're modern day stone knappers. And so he had a pile of lithic microdebattage and a pile of regular soil. That's a machine learning problem. That's a data science problem. And that entirely changes the need for the access to this data. So the data looks like this. What he wanted was to be able to read all this data in and to get something out that looked like, rather like this. Is this lithic microdebattage? Yes or no? For each individual, each of the millions of particles, just give a yes or a no. So at no point, actually, do you need to go and directly access and get the properties necessarily of particle ID number 85, which, by the way, is the last line right here. You don't need to do that. Instead, what you need to do is you need to have a judgment, yes or no, and the probability that it's a lithic microdebattage or not. So it turns out that if you're doing that kind of work, then it makes really good sense to leave the data in as raw a format as possible. Leave it as a CSV, because you run a sample from one location. So you've run a sample and you've run the sample and you got this sample from, let's say, this area right here. That's one file. You leave that as one file, and then you read it into R or into Python. So in this case, reading it into R and Python, we can actually do this together. Rather than trying to load it up into a database, rather than trying to load this up into Excel, you write some R code. And actually, he and his teammates learned how to write R code with us. You store all of the different samples that you have, a couple of hundred different samples, but store them all into a box, which is locked and is available to your research group. And this right here is where we actually read all those lines in all at once. We're going to run this. You're going to see how fast it is. And we're now done reading the data. So imagine how long that would take to read into Excel, or imagine how long that would take to read in using a database. Databases can be expensive. So if you need to use them, absolutely do. But data science, and whenever it's a machine learning or deep learning problem, it's designed to read in these types of files very, very quickly. How much can you read in? I've read in data sets that are about 200 million rows, and without too much of a difficulty. We've since actually rerun this and rewritten this to use Python instead, because he was interested in a slightly different approach. But all the other aspects that we were just discussing can be done at the file level. So if you need to do securing or curating, you're curating at the file level. So you name the file according to a rubric, so you know exactly when it was taken, where it came from. You have a separate table where you list all the different files that you have. Preserving the data actually consists now of saving those individual files, perhaps zipping them up and putting them into a safe place. But it's a very different type of problem that we ended up solving rather than trying to stand up a database. So finally, I'll leave you with this view and what this can result in. So the final work actually turned out to be a repository, which include all of the code necessary to read the data in, to work with the data. The data itself can be versioned, just like the code can be versioned. And now, whenever he needs to share this research, he can share the repository, share the data, reproducible science that is also open science. And it all came from about choosing the right format and the right way to store data. And I'll pass this on now to our next presenter.